Hello everyone. In this video, we will be talking about skewness. So basically, skewness determines the asymmetry of a data set distribution. So it tells us about how the data is being distributed around its mean. So it indicates the data points are symmetrically distributed or they have a tendency to move towards a particular direction of the distribution. So it's one of the very important part of the data analysis or exploratory data analysis, especially when understanding the shape and characteristics of a data for tasks like modeling or if you are doing any kind of a regression machine learning problem in case of forecasting also, so it's very much important. So there are different types of skewness. So first one is the symmetrical distribution, or we can say zero skewness. So when we talk about zero skewness, in this case what happens is like the mean is equal to median, or the ace or the symmetric distribution of zero skewness refers to the normally distributed data. So it's like a perfect bell curve. So in this case the skewness is close to zero, and the distribution we can say is roughly symmetrical with data points evenly distributed around the mean. So, and this is a kind of an example of a normally distributed data. So then comes negatively distributed data, which is also called as the left skewed data. So you can see here on the left side, this tail is much more longer. Here in this case, median is greater than mean, and the most data points are being concentrated on the right side with the fewer lower values pulling the mean to the left side. Okay, so this is an example of a negatively skewed data, negative skewness. um, Next is the positive skewness, or we can say the right skewed data. So a positive skew indicates that the tail is on the right side. It's being much longer. You can see here it can go much longer. Okay, so here in this case, what happens is like the mean is greater than median, and most of the data points are concentrated on the left side, but the extreme values are on the right side, which pulls the mean to the right side. So this is about the positive skewness. So the next thing is we will look into what the skewness tells us about the data. Like if there is a skewness present, what we can interpret from that particular skewness. So first thing is like it helps us to understand the outliers. So if there is a skewness in the data, whether it's a left skewed or right skewed, we can tell that there is some kind of an extreme values. These extreme values can be on the negative side. It can be on the positive side also. So skewed data often contains the outliers that affects the mean, and it makes it less representative of the data as a whole. So skewness, when there is a skewness, so we need to handle it in a we need to handle the outliers according to the assumptions of the algorithms. So next is the mean median relationship. We saw in the previous diagram that when it's a negative skewed data, so median is greater than mean. Positive skewness, so mean is greater than median. And when there is a normally distributed data, so mean is equal to median. So it also tells us about the relationship between the mean and median. The other thing is the statistical analysis. So there are a lot of machine learning models, for example, linear regression model, then certain statistical tests, and those statistical tests are called as the parametric test. So these tests is based on the assumptions that the data should be normally distributed. It should not be skewed. So whenever we are doing any kind of linear regression model or any other statistical model, we need to check that there is if there is any skewness present or not. If there is any skewness, then we have to convert that particular data into a kind of a normally distributed data. Okay, because skewness indicates deviation from normality, and it we can say that it can guide the analyst to apply transformation or alternative models in case if it is being required. Next thing is about the determining the central tendency measures. So sorry. So for a skewed data, we know that whether it's a positive skew data or negative skew data, mean tends to shift. Okay, mean is not in the middle. So in that case, whenever there is a skew data, median is being considered as the measure of the central tendency than mean because it is less affected by the extreme values. Uh, so this is about the things. Okay, now there are different ways in which we can calculate the skewness. So skewness can be calculated by the first one is um, uh, Pearson first coefficient of skewness. So this is being given by the formula where mean minus mode and divided by the standard deviation. So this is very much useful when you have a kind of a unimodal distribution where distribution with one peak is there and where mode is being well defined. So in that case, you can use the Pearson first coefficient value. Then we have the Pearson second coefficient value. So it is given by 3 multiplied by mean minus median divided by standard deviation. So it's very good to apply, especially when there is no mode. Okay, you don't have the exact way how to find out the mode. So in that case, this formula second coefficient is much more better. Then we have the Fisher skewness, which is also called as the moment skewness, or sample skewness. So here it is being given by 1 by n, where n is the sample size. Then xi is the each individual value, summation from I to n to the sample size, minus mu here is the mean divided by the sigma is here is the standard deviation raised to the power 3. This Fisher skewness is commonly used because it measures the asymmetry of the distribution around the mean, and it's useful for data sets where outlier might affect the symmetry. So whenever there is an outlier, presence of outlier, it's better to go for the Fisher skewness. Then we have the adjusted Fisher-Pearson standardized moment coefficient. So so this is also given by the under root n multiplied by n minus 1, where n is the sample size, divided by n minus 2, multiplied by summation I is equal to 1 to n. Then xi, where xi represents each data point value, minus mu. Mu is here is the mean raised to the power q, divided by standard deviation raised to the power q, multiplied by n. So this is how we can calculate the adjusted Fisher-Pearson moment coefficient. Okay, so this is like a kind of a more adjusted one, is the more accurate measure of skewness, and it's very useful when you are dealing with the small samples. It adjusts Fisher skewness to provide the unbiased estimates for smaller data set. Next is the Bolly's skewness. So Bolly's skewness is like Q3 plus Q1 minus 2 multiplied by median divided by Q3 minus Q1. So where Q3 represents the third quartile, which is the 75th percentile, and Q1 represents the 25th percentile, and median is the median. So this is how you can calculate the Bolly skewness. So Bolly skewness is helpful when you have a kind of a non-normal distribution of data with outliers, because since it's based on the interquartile range, so whenever there is an outlier, you can go for the Bolly's skewness. Next is the Cayley's coefficient of skewness. So Cayley's coefficient of skewness is given by P90 is the 90th percentile plus P10. P10 is the 10th percentile minus 2 multiplied by P50. So P50 here is the median divided by P90 minus P10. So P90 is also the 90th percentile. P10th is the 10th percentile. So this is the more kind of a non-parametric approach to skewness. It is especially useful for when you have a very huge data set, or data sets where percentile-based calculations are preferred over the mean-based approach. So, uh, so, so this is how we can do that. So next thing is like how to choose the right metrics. So whenever we talk about symmetric data with defined mean and median, so we should go with the Pearson coefficient. So whenever there is a data is normally distributed data, so you can go with the Fisher skewness. And when there is a smaller sample size, when where the sample bias needs to be minimized, so then you can go with the adjusted Fisher-Pearson skewness. And if there is a skewness in the data, or where the outliers are being present. So in that case, you can go with the Bowley and the Kelly's skewness method. So this was all about the skewness. Please let me know if you have any questions in the comment section, and let me know if you need any additional topics related to this. Thanks everyone. We will talk afterwards on the next video. So.